Let's practice some medical physics questions. As always, there are links to the questions in the description of this video. Okay, so the first question is about an X-ray scan. The X-rays interact with atoms in the patient. Name and describe the three methods by which X-rays interact with matter. Okay, so first of all, we need to name them and then we need to describe them. Shall we start with the photoelectric effect? So I'm just going to write here the photoelectric effect. Now, in the photoelectric effect, we have a photon which interacts with the atom and then it ejects an electron. The next one is known as Compton scattering. So Compton scattering. And with that, the photon still interacts. However, there is it emerges with a lower energy, meaning a longer wavelength. So we can just say that the photon interacts with the electron and emerges with a longer wavelength. We can also write just a lower energy, so I'm just going to put this into brackets, lower energy. And in this case, one more time, an electron is ejected. So an electron is ejected. We have one more, which is pair production. And with pair production, we actually have a photon which actually disappears. And so we can just say this, the photon disappears and a pair of an electron and a positron are produced. Okay, part B, we have a radiographer that uses X-rays of a certain wavelength, 1.4 times 10 to the power of minus 11 meters, to investigate how the intensity of the X-rays transmitted through bone varies with its thickness. And we have a figure which shows the graphs of Ln of I against X. So just looking at this figure, first of all, I'm going to note that here that the units are in centimeters, which is probably going to be important later on. Looking at the Ln as well, I probably know I'm going to be using y equals mx plus c analysis later on. Okay, first question, not too bad. Calculate the energy of a single X-ray photon of this wavelength, where this is 1.4 times 10 to the power of minus 11. If I have the wavelength, I'm going to use the trusty E is equal to hc over lambda equation. So it'll be 6.63 times 10 to the power of minus 34 multiplied by the speed of light, which is 3.0 times 10 to the 8 meters per second, divided by the wavelength, which is 1.4 times 10 to the power of minus 11. And calculating that, we're going to get approximately 142, let's call it 14 times 10 to the power of minus 14 joules. Now, the next part, use the figure to determine the absorption attenuation coefficient of the bone. Okay, so we have a graph of Ln of I against X. So my first step would just be to rearrange my equation to whatever is on the y-axis. Because the equation is I is equal to I naught e to the minus mu x, then what I'm going to do is I'm going to bring this over to this side. I'm going to say I over I naught is equal to e to the minus mu x. Now I'm going to take the natural log of both sides. I'm going to say Ln of I over I naught is equal to Ln of e to the mu x. Now Ln and E are inverse functions, so what I get is Ln of I, and also I can just say minus Ln of I naught, because if it's the Ln of a fraction, this is equal to Ln of the top bit, take away the Ln of the bottom bit. And this here will be equal to minus mu x, meaning that Ln of I will be equal to minus mu x plus Ln of I naught. Okay, well, if this thing is on the y-axis, we're using y is equal to mx plus c analysis. Our intercept will give us the initial intensity, or the Ln of the initial intensity, and our gradient will be the negative absorption coefficient. So all we need to do is to ensure that we have a large enough gradient and calculate it. Now, just keep the video brief. The range for our answer from the gradient will be somewhere between 0.19 all the way up to 0.21 centimeters to the power of -1 for the attenuation coefficient. So if you've gotten a value anywhere between those two values, you're good to go. Okay, on to the next question. So briefly describe the process of pair production in terms of X-rays, photon interacting with the atom. So essentially one mark again from the question we did previously, and we can just say that the X-ray photon disappears, and an electron-positron pair is produced. Electron-positron pair is produced. They actually annihilate shortly afterwards, and remember when I was a student working in a nuclear lab, this was one of the most recognizable symbols that your detector would pick up, or one of the most recognizable energies that a detector would pick up. Okay, on to part B. High-speed electrons hitting a metal target in X-ray tube produce X-ray photons. Calculate the accelerating potential required for an electron to produce an X-ray with a maximum wavelength of 18 picometers. So I'm going to use EV is equal to HC over lambda, and because we're looking for the accelerating potential, this of course means that V will be HC over E lambda, which is going to give us 6.63 times 10 to the power of -34 multiplied by the speed of light, 3.0 times 10 to the power of 8 meters per second, divided by the electron charge, 1.6 times 10 to the power of -19. And so pico is -10 to the power of -12. So 18 times 10 to the power of -12. That's going to give us 69062, 2 sig figs, call it 6.9 times 10 to the power of 4 volts. Okay, part C, we have a uniform beam of X-rays with a certain intensity, 2 times 10 to the 8, is used to destroy cancerous cells in a patient. The beam has a cross-sectional area of 6 millimeters squared, and the cancerous cells are at a depth of 1.1 centimeter in a muscle. We're given the attenuation coefficient, which is 5 centimeters to the power of -1, and the radiographer estimates a total exposure time of 2 minutes to destroy the cancerous cells. Calculate the total incident energy. Okay, so my plan of action is to use the attenuation equation, so I is equal to I naught e to the minus mu x, to work out my intensity. After I have my intensity, I can just use the fact that intensity is power over cross-sectional area. So I could work out the power by just multiplying them out. And after I have the power, I can just work out the energy simply by using that power is energy over time, so therefore energy is going to be power times time. Okay, well, let's do this. So I will be equal to our initial intensity, which is 2.0 times 10 to the 8. So 2.0 times 10 to the power of 8 multiplied by e to the power of minus, and the attenuation coefficient is 5.0 and multiplied by a depth of 1.1. Okay, well, putting this into a calculator, we're going to get 81735. So let's give it quality of accuracy. So 8.174 times 10 to the power of 5 watts per square meter. Okay, we have the intensity, so let's work out the power. So we're going to work this one out. So power is just intensity, which is this number, 8.174 times 10 to the power 5, multiplied by the area. I'm just going to be quite careful converting the millimeters squared. So the power will be 8.174 times 10 to the power of 5, multiplied by 6. Now, milli is 10 to the power of minus 3, and then it's squared as well, so it's going to be 10 to the power of minus 6. And putting this into a calculator, we're going to get around 4.9 watts. Okay, we're almost there. All we need to do is work out the energy, which is 4.9 times the time, which is 2 minutes. So that's going to be 2 minutes with 60 seconds each. So let's multiply this out. So 4.9 times 2 times 60, which is going to give us 588. Let's leave it up to two significant figures. So it's going to be 590 joules. Okay, next question. Describe the piezoelectric effect. Well, when we apply, or when a PD is applied to some crystals, the material, let's say, will expand, or it may actually contract. Just to ensure to get full marks, even though I'll probably get full marks with this, I can also say that if the voltage is AC, the object will oscillate. So we can say that the object will oscillate. Okay, an ultrasound transducer produces pulses of ultrasound. Figure 7.1 shows the display of an oscilloscope connected to the transducer. Okay, so that's the pulse of ultrasound that we can see. We have the scaling over here. The transducer is now placed on the skin of a patient's arm to determine the thickness of the muscle as shown. And now we have a new display, and the two figures are different. So we can see that there's some new peaks that have emerged on this ultrasound scan. And the first question to explain why the two figures are different. Now, because there's some gel over here, we can say that there's definitely some reflection at this boundary over here, which, so as soon as the ultrasound, it goes through the gel, then goes through the skin, then comes back here, and this corresponds to this peak over here. So we can say that this corresponds to reflection from the, is it the bone and muscle? Yeah, the bone and muscle boundary. Bone/muscle boundary. Okay, the speed of sound of the ultrasound in the muscle is 1,600 meters per second. That's pretty quick. Use the figure to determine the thickness of the muscle. Now this here is actually a classic question which has a catch. Let me just show you what the catch is. So we can see that the reflection happens in 20 microseconds because we can see that this is the scale. So this means that the width of one of those squares is, well, 20 microseconds. However, in order to get a signal here, we've actually traveled the distance x twice, because the signal goes there once and then comes back, essentially just like this. So what we're going to say is that 2 times x is actually equal to our speed times time, so vt. So 2x is the speed, which is 1600, multiplied by the time, which is 20 microseconds, which is 20 times 10 to the power minus 6, meaning that x will be 1600 times 20 times 10 to the power minus 6, divide that by 2, and what will this give us? Around 0.016 meters. Okay, next one, the acoustic impedance of the muscle is 1.7 times 10 to the power 6 kg m to the power minus 2 s to the power minus 1. Calculate the density of the muscle. So the acoustic impedance Z is equal to rho C, where C is the speed of sound in that particular medium. Looking for the density, which is going to be Z over C. So what is that? 1.7 times 10 to the power 6. This C here is not the speed of light, it is the speed of the ultrasound in this case, which is 1600. And this is going to give us 1.1 times 10 to the power of 3 kilograms per meter cubed, which seems like a pretty normal density, so we're fine with that. Okay, next one, acoustic impedance. The fraction of the intensity of the ultrasound reflected at the bone muscle boundary is 40%. The acoustic impedance of the bone is greater than the acoustic impedance of the muscle. Calculate the acoustic impedance of the bone. Okay, so I'm going to use the fact that the reflected intensity over the original intensity is just equal to Z2 minus Z1 squared over Z2 plus Z1 squared. Okay, well, this fraction here is 40%, which is just 0.40. Let me just double check there's not 60. The fraction of the intensity of the ultrasound reflected, yeah, that's fine, it is 40, is equal to Z2 minus Z1. Okay, well, we actually know what Z1 is because it was given in the question. So the acoustic impedance of the muscle is 1.7 times 10 to the power of 6. So this will be equal to Z2 minus, wait, I've forgotten the value, 1.7 times 10 to the 6, 1.7 times 10 to the power of 6 squared, and then I'm going to divide that by Z2 plus 1.7 times 10 to the power of 6 squared. Now what I'm going to do, just to ease things a little bit, is I'm going to square root both sides to get rid of those squares. And let's find the square root of 0.4. Okay, so it's around 0.63. So 0.63 is equal to Z2 minus 1.7 times 10 to the power of 6 over Z2 plus 1.7 times 10 to the power of 6. Okay, now let's bring this over on the other side, and what we're going to get is 0.63 Z2 plus 1.7 times 10 to the power of 6 is equal to Z2 minus 1.7 times 10 to the power of 6. I kind of wish I'd left this now as a Z1 in the algebra and then only written it once, but hey ho, we've started already. Okay, so let's expand this, so 0.63 Z2, then let's take away a Z2 2 from the other side, and this will be equal to minus 1.7 times 10 to the power of 6, and we're going to take away the factor of 0.63 times 1.7 times 10 to the power of 6, like this. And Z2 can be factorized. Please let me know if I'm doing this, if I'm overcomplicating this, if you spot an easier method. We're gonna have 1, or excuse me, we're gonna have, if I take away Z2, we're gonna have 0.63 take away 1, and that is equal to all of this, which is minus 1.7 times 10 to the power of 6 minus 0.63 times 1.7 times 10 to the power of 6. And Z2, final calculation, quite intense algebra for 3 marks, this will be equal to minus 1.7 times 10 to the power of 6, take away 0.63 times 1.7 times 10 to the power of 6, and divided by 0.63, take away 1. Actually, I'm going to do one change before I put this into a calculator. Rather than 0.63, I'm just going to type in my calculator the square root of 0.4, just because this function can change really rapidly. So I'm just going to write square root of 0.40 here, and here as well. Hopefully I don't mess this up. So square root of 0.40, okay, times 1.7 times 10 to the power of 6, and this here was a minus sign. Okay, and when I put this into a calculator, I get 7.55 times 10 to the power of 6 kilograms per meter squared s to the power of minus 1. Now in this question, I'm working up to 2 significant figures. Yep. So I'm just going to say that this is equal to 7.6 times 10 to the power of 6 kg m to the power of minus 2 s to the power of minus 1. Okay, question 8 from the next paper. We have the radioactive gamma emitting tracer technetium-99m was injected, and this here is a picture of a gamma camera scan. Discuss the advantages of using a gamma emitting tracer in the patient rather than a beta emitting tracer. Now the obvious one is that gamma emitting tracers will pass through the body of the patient producing an image. So can just say, so the gamma rays, the gamma particles will pass through the patient, and this will of course allow for an image to be produced. So we can just say producing an image. Of course, we can also say that the beta particles will actually be absorbed. Now, additionally, the gamma rays or the gamma particles are actually the least ionizing. So we can say that the gamma particles are less ionizing than the electrons or the beta particles, like so. Okay, two marks, 2 things written. Moving on. Many hospitals are equipped with CAT scans. Describe how the components of a CAT scans are used to produce a 3-dimensional image of the patient. So with a CAT scan, I've just removed what I've just underlined here. We are using an X-ray tube, and that is actually rotated around the patient. So it's rotated around the patient. It's also really important to note that a thin X-ray beam is actually used, like so. Then what we have is that an image of a essentially a slice or a cross section of the patient. Is taken. Okay, and this image is actually analyzed by a computer to produce a 3D image. So what actually happens is we take one cross section, and then the X-ray tube moves. And essentially it moves around the patient. Let's say that around the patient, and further images are taken. Now all this data is sent to a computer, so we can say that the data is used by a computer to produce a 3D image. Okay, so that's 5 marks. 1, 2, 3, 4, 5. 5 pieces of information. All good. Okay, so next we're looking at just a part of a question, because this keeps coming up very frequently in exam. Describe how high-frequency ultrasound can be used to determine the speed of blood through the arteries of a patient. Okay, in your answer you should make it clear how the speed is determined. Okay, so the first thing we need to write is that we have a transducer is used to emit and receive ultrasound. And also it is actually placed, and it is placed at an angle, and this is really important. Placed at an angle. So what happens then is that the transducer emits some ultrasound, and then ultrasound is reflected by the blood in the artery. And then afterwards it's received by the transducer. Then the equation that which is given in your formula sheet, by the way, delta F over F is 2V cos theta, don't forget the factor of 2 here, divided by the speed of sound C. And this equation is actually used to determine the speed of the blood, which in this case is V. Now in this equation, it's always useful to define all the quantities. C is the speed of sound. Delta F over F is the fractional change in frequency, so fractional change in frequency. And theta is just the angle. So we can see why it's important to place the transducer at an angle, because if theta is 90 degrees, this expression will actually turn to 0. But this is a very common question, and it's good to revise it. Okay, next question. Figure 8.1 shows a B scan image of an ultrasound scan, and describe and explain the principles of a B scan. Okay, so we can always start the ultrasound questions by saying that ultrasound is being reflected at each boundary. So we can just say that ultrasound is reflected at each boundary. or each tissue boundary. Now the B scan is specific for the B scan, unlike the A scan, which is one-dimensional, takes place in multiple directions. So the B scan takes place in multiple, or should we just word this a little bit better and say that the B scan is repeated in multiple directions? Quite often on the mark schemes you can say that, I'm going to write this in bracket, that a B scan is multiple, forgotten to finish this word, is multiple A scans, like that. Okay, so the ultrasound is reflected at each boundary, the B scan is repeated in multiple directions, and after a transducer emits some ultrasound, is reflected at each boundary. What the transducer is actually measuring is the reflected intensity. So we can say that the reflected intensity depends on the acoustic impedance of the tissue. Finally, just for completeness, this is the same mark. I'm pretty sure I would have scored 3 marks with this. We can also say that an image is produced, or a 2D image is produced by a computer. Always safe to say that in questions like these. Okay, on to the next one. Figure 8.2 shows an image of the brain. How interesting, using a PET scan. So the lighter regions show the active areas of the brain. Fluorine 18 is a common tracer. Explain the basic principles of the PET scan, including how an image is formed. Now, with a PET scan, the patient is surrounded by a ring of gamma cameras. Patient is surrounded by a ring of gamma cameras. Like that. Now, because the patient is injected with fluorine 18, which actually emits a beta plus particle, which is a positron, we can say that positrons from the fluorine 18 annihilate with electrons from the body. Now, when that actually happens, you have two gamma ray photons are actually produced. So we can say that two photons traveling in opposite direction. This is really important. They travel in opposite direction just to conserve momentum, by the way. The photons traveling in opposite, two photons traveling in opposite directions are produced. Then we actually use the delay time to produce an image and to actually locate the position of that event. So we can just say that the delay time of the photons is used to determine the location of the annihilation. And finally, all of this is connected. The gamma detectors are the ones that actually locate the photons, are connected to a computer. And an image is formed. Okay, brilliant. Okay, the final question of today: name and describe the function of the main components of a gamma camera. So let's start off with the collimator, which consists actually mainly of lead tubes, and the purpose of those lead tubes is to absorb all gamma photons or gamma rays, gamma photons, which are not parallel. And then afterwards we have what is known as a collimated beam, hence the name of, so after the collimator, the beam consists of parallel gamma ray photons. Okay, the next one is the scintillator. Now this is typically a sodium iodide crystal, and the main purpose of it is to essentially get the gamma ray photons produce visible light. So gamma ray photons produce visible light photons. And the tricky bit that we need to mention here is that one gamma photon, because of the difference in energies, one gamma photon produces many visible light photons. Okay, up next we have the photomultiplier tubes as a part of the gamma camera, and the visible light photons actually produce an electrical pulse. Let's call it signal actually, an electrical signal. The final part of the gamma camera is of course a computer, and we can just say that the signals from the photomultiplier tubes are used to produce an image. Okay folks, well, this was only part of the medical physics. I've tried to do quite a lot of problems, but in order to revise fully, you absolutely need to have a look at my medical physics video, which I cover most of medical physics, and this video is just over here.